So our next speaker is Mike West from Duke University. So I just want to mention for people who are still around on Friday, so Mike is giving one of the Turing lectures at the Alan Turing Institute in London, so on Friday afternoon. So on structured dynamic graphical models and scaling multivariate time series. So it's 3 p.m. At the British Library.
Yeah.
On Friday. And so this morning, so we'll talk about joint work with Rob Aslinger and Jewel Thomas on Bayesian dynamic modeling of networks.
Thank you, Francois. Thanks for slotting me into the program. What a lovely meeting. It's a very diverse audience, and what I have here is just some basic applied statistics, and really the talk is about 3 principles. I do a lot of time series and dynamic models, so some has to do with that. The first principle has to do is also represented in the Turing talk, which is a version of the talk I gave at the machine learning group last week. Some of you will have seen. So these are some good friends who have tons of data in quite an old, nearly 10-year-old company. Got into the business of e-auctions and ad placement and so forth. One of the most active companies in the world in that area. And this is this work is this paper about a year ago is a little piece of a series of interlocking projects, a lot of which are networky. So the context here is I think probably the first talk in the workshop about stuff moving on a given network. The network is there. We define the network, or they define the network, and we're interested in characterizing variability of data as it flows through this network. Okay. Very simple statistics. We want simple models. And we're in a sequential context. We're looking at data in time. And they want to do this on large networks. Okay, so there's some imperatives here that drive the thinking and help you define the desiderata that you want your models to grow from. And then, of course, you're interested in more complicated structure, cross-network relationships and how they vary in time. And that will hit on a second principle of using simple models to emulate more interesting structured models. And the term emulation comes into play there. Okay, so the network today is 22 or 23 nodes, very small network. The current work 3 months in now with a 2,400 node network on half-minute data, just continuing in time, but that's not ready for prime time yet. Okay, so here are the 3 principles. So those of you that saw my talk or participated in my talk on Thursday, there were lots of good interaction, will have heard me use the term decouple recouple. Okay, and I got into this in a very different context a year or 2 ago because I decided I was sick of doing MCMC and complicated variational stuff and all of this big hard computation and complicated high-dimensional multivariate models of interesting systems, because that was absorbing 99% of my time and effort and my students' time and effort. Okay? So I said, well, let's go back to basics and be simple and do mathematics as much as we can. But let's be careful and thoughtful about how we then tie things together again for the whole multivariate system. Second point I already mentioned, if you do take that view, decouple things into lots of little pieces, well, usually you'll be using little pieces that don't look like the model that you want to fit. Okay, so let's call it an emulator of the model you want to fit, and let's figure out how to get back there somehow. Bayesian model emulation. The last point, I may not get enough time on this, but it's just not just so much as a principle, it's just a feature of sequential analysis in forecasting systems. This is not about forecasting, this is understanding dynamic variation through time. Is that of continually being involved in where the model's going and how the data looks with respect to the model, and being ready to jump in and change things, or having some kind of automated system to allow you to do that based on principles. Okay, so Mike's point is in the business, many businesses actually, that putting ads on websites is their core business, but more than half of their revenue comes from other things, like watching you in Sainsbury's when you're walking around with your cell phone looking for the best deal on a particular wine. They have tons of interesting data of that kind. But they're interested in, what happened when we place those ads, because that's how they sell ads to customers. So We're not in that stuff today, but that's the background. If you're looking for sort of, quote, causal inferences from that kind of data, where they've had the opportunity to do some quasi-experimentation, you first need to be pretty sure you've got a good basis for the models that you're going to bring to that data, i.e. you understand what normal stuff looks like pre-intervention. And although there's a ton of work in this area, there's the recommender systems and related areas, there's actually very little work, published work, on just basic statistics. What does this stuff look like in normal conditions? So here's the network. These are 22 nodes. And the way this works, this is Fox News. This is the home page. And these are the 22 domains that are directly below Fox News, Fox News/X. And there's thousands of other pages. That's where the 2400 website node network comes from. So we call they call these domains. Okay, and these colored balls just represent current occupancy. How many of you are actually looking at the home page of Fox News at this instant? Okay, 30-second instance through the days, many days. The data today is just from a couple of hours, morning and afternoon. And the way they do this is that they look at clicks. They've got all of the click data. They've got refresh data. They've got user refresh data. They've got automated refresh data. Are you still there? Pinging the user. And then they have there's quite a big literature on people's staying power. 5 minutes is it. So if you refresh, you're not there, you're gone. So that's how they figure out that you've left the page if you didn't appear somewhere else in the network. Okay? So for us today, we've just got a given network, and I'm going through a few half-minute periods here, and you see some changes as we go through. Probably can't see it very well, but the shading of gray runs from very light to black, just the density of the flow in that instant. So there's a lot of sparsity in the flows. There's a lot of pairs of nodes that in any given instant any given half-minute interval don't have flows. And then there are busier flows. There's a 23rd node which is outside the network. Okay, that's node 0. Okay. So here we are. So I'm going to speak to the slides here. One class of very simple models. The simplest model for a time varying Poisson rate that has any utility. It's simply smoothing the data. There's lots of data that is 0. Okay, there are lots of flows at any given instant that are 0. Okay. There's lots of flows that are very high. So we want a model for smoothing, and that is a fully Bayesian model that operates sequential in time, modulo the desiderata of scalability, efficiency, and decoupling, so we can do things fast in parallel with bigger networks eventually. Then I'll talk about a slightly more structured model. So this is node I. N is the current occupancy. So these are numbers, non-negative integers. And these are the flows out in the next time instant to the other nodes, including the 0th node, which is outside that network. And there's an inflow. So the first index is the node. The second index is the receiving node. And the third index is time. Okay? So what are these? Well, we'll start with the inflows. So there's inflow to any node. We're going to have a set of completely decoupled Poisson models. Okay, I learned the term Poissonization this morning. Well, you don't have to Poissonize this. It's compound Poisson, but this guy will vary, so there's some compounding in there. Where there's some underlying Poisson mean that is going to drive the model. And how are we going to think about that? So this is the first stochastic volatility model ever published and used in finance, and it's still the cornerstone of tons of financial volatility models, pieces of much bigger models. Call it a stochastic volatility model, but here it's being used for Poisson rate. So it's a log linear model for a Poisson mean, okay, where the transition from t minus 1 to t is basically a random walk on the log scale. There's plus log nu it, okay, so it's a multiplicative random walk. And it has the feature, and that's why it's interesting, modulo the first desiderata, that if these guys here, the new IT, these are instantaneous innovations independent over times and nodes, if these have the right beta distributions, then starting at time 0 with the right gamma distribution, as you move through time, you maintain gamma structure of a particular, in a particular part of the analysis for these phi's. So it's a gamma beta multiplicative random walk. The stochastic volatility model, it's used for variances or precisions of returns of financial indicators, which we've used for 35 years since it was published. You know, it's a sort of random walk. It's a random walk. It doesn't predict variation in these rates. It just tracks them. So it's okay for monitoring and understanding, you know, how much are these things varying, and from one period extrapolation to just test the consistency of the data with the model, but it doesn't predict. Okay? So it's a model that will allow with a very stable version, sort of, you know, it'll go to flat trajectories, but it will also allow more erratic drifts and trends depending on the level of volatility coming in through the innovations. Okay? And it's controlled by a single parameter. There's a single parameter, and this can be node specific. And you can take your training data and play about with it and put priors on that parameter and learn about it and think about how it might change with time as well, but that's not for today. Okay, so we can decouple across nodes. We can run analytic forward sequential analysis. We call that filtering in time series, one-step forecasting that leads into monitoring. Forward filtering then, at any instant t along the time axis here, we've got data at node I, incoming flows to node I up until that time point, and there's a posterior distribution at that time for the current rate, which happens to be a gamma distribution in this model. So it's trivially computed the way that the parameters of that gamma change in time. And then when we get to the end of the period, in our example, the data is an hour long, 120 time points, and look back over time and said, well, what was the phi process over time? We call that smoothing in time series. And we usually look at that by simulating the history of the process from the posterior distribution. Backward or retrospective sampling. So it's a sort of forward-backward algorithm where you recapitulate the entire process. And it's trivial. I mean, it's, you know, you do it on your cell phone in a fraction of a second. Okay? So even if you've got 2,400 nodes, that's an easy bit. Okay? I don't want to do big Monte Carlo computations. I'm okay with just, you know, generating a few gamma random variates for a direct posterior sample. Okay, so some of the guys look smooth. This flows into the leisure domain over one of the morning periods with the actual data. All we're doing is smoothing the data. Forward in time, it's slightly erratic. This is the one-step ahead forecast mean with a 95% one-step prediction interval. So this is a negative binomial distribution projecting every time. And then this is how we're tracking phi, the posterior 95% interval and mean, coming contemporaneously through time. We look back, it's smoothed out. Okay, so there seems to be a drift down in the traffic in this period. That's a very boring example. Here's a more interesting example, the inflows to the world domain. All right, people go to Fox News, actually want to hear about things other than the Republican election stakes. They actually want to hear about the world as well. About halfway through this morning period, this is about 9:30, things begin to tick up, and the model obviously isn't doing so well there. The online posterior is tracking it, but it doesn't respond fast enough, and you get a clear increase over the period. So this is a short-term tracking model. If anybody does time series, it's a gamma exponential smoothing kind of technique, but it's wrapped up in a full Bayesian analysis, so you have access to everything that you need, full posterior uncertainties.
Yeah, so in the raw data on the top panel, I see a few modes that get smoothed out. Is that something I should be worried about in the model, or?
Yeah, you should be worried about this. Obviously, you should be worried about this. it's crummy at that point, all right? All right, absolutely crummy. You should be worried. You're coming forward in time, you see stuff, the model doesn't predict it, stop, do something. I'll come back to that, that's under the third principle. Okay, so now we go to the rest of the, so that's the network on one node. We've dealt with that. Now let's go to the rest of the network where we're sitting in this node and stuff is going to leave in the next instant. Well, it's multinomial. Well, I've got 2,400 nodes in my real network right now. So I'm not going to do 2,400 dimensional multinomials, right? How are you going to do that? How are you going to build a model of that? Okay, decouple. So there's the multinomial with a set of cell probabilities on node I leaving this node. Well, multinomials come from Poissons, right? Poissonization. Independent Poissons add up, and then you scale by the sum, all right? And first of all, the difficulty in this context is, and secondly, a real positive feature of this context is that you don't know the scales, right? When you take Poissons and add them up and divide by their sum, there's an arbitrary positive number multiplying the individual underlying Poisson rates that cancels when you get the multinomial probabilities, all right? So we really, all we want is a model on the probabilities, but we're not going to do that. That's just too big. Okay, so that each outflow from node I to node J is a conditional Poisson with some Poisson mean, node ij dependent, varying over time. We want to track that, and some arbitrary positive scale that is labeled by the sending node. So you can choose it. You can choose 3 or 1. Or you can remind yourself that what you're really doing is looking at proportions flowing out, okay, and we've mapped over to counts in the decoupled models. And if the occupancy of the sending node suddenly triples this interval, your outflows will triple, okay, even if the probabilities, relative probabilities, are the same. Okay, so you can creatively use that unknown constant there. Let me put the whole thing down here. That unknown constant there, we call it the occupancy factor, to deal with that. It's your choice. So our models simply rescale the Poisson means based on the occupancy. And then for the rest of it, we use the same volatility model. There's nothing now different. We've come to a Poissonized set, or a set of decoupled Poissonized Poisson models, and we'll apply the same model. So then we can recapitulate the earlier slide. We're now tracking these probabilities coupled over time. Again, it's completely decoupled overall pairs of nodes now, and then we'll recouple when we want to. Because we're using the gamma beta random walk, forward filtering, backwards sampling on each of the phi ijt's, trivial. And then when we come back and do that Monte Carlo simulation of the history of the phi's, we simply compute the multinomial probabilities. So we get direct, full, exact posterior distributions via direct simulation. Let me skip ahead a little bit since time is a bit. What time did I start, Francoise? There was some preamble and some messing around over here. 12 minutes? Okay, I'll have to cut short some of the pictures. All right, so there's a daily pattern. This is, let me skip over inflows. This is just inflows, the phi's inflowing to the outflowing from the home page to the external. This is from home page to entertainment. Daily pattern. These are the phi's for these very narrow intervals. There's tons of data here, although lots of the flows are sparse. Lots of them are non-sparse. And the only point worth noticing here is this. It's sort of moving towards, well, how do these things get used in practice? We want to understand what happened when we placed these ads, or what happened when this whole website was reconfigured, or what happens when our competitors came in and placed these ads. You like to overlay labels on some of the differences that you see, like big spikes and things relative to known events, for example. Okay, so recoupled with a multinomial, okay? You haven't got a cat in hell's chance of building models for even 23-dimensional multinomial time series using any kind of Dirichlet structure. It's going to be very much more complicated multivariate log linear models, okay? Which is sort of what we've got, them decoupled, okay? Very, very simple. But we want to think about moving to more structured models. There's lots of covariate information for these nodes. Nothing today, except the name, but that's what we, part of what what we're about. So we'd like to think about, well, let's look at dependencies, okay? Let's look at cross node dependencies. So this comes to the model emulation part of the talk, the second principle. Here's a different model. Let's suppose you like the idea of Poissons. Well, you're going to want to structure those things. What do we, at least 4 people have used the row and column analogy in previous talks this week. So let's, instead of thinking these are just free guys wandering through time, let's think about their dependencies. Let's think about overall levels at any given time of traffic, and let's think about sender effects. Node I is sending stuff out at some rates that are changing over time, alpha IT for node I, and receiver effects, and then interactions. Okay, and in general, these can be labeled with not only the name of the node I, but covariate information. Okay, the things that we did to that web page overnight, the ads that we placed there in the instant before, the markets opened. The information that describes and is updated through time where the people in that node are coming from. The occupants at any given time, some come from the northeast US, some come from Shenzhen region of China, some come from Sydney region of Australia, and all that information is in there. Not in our data today, it just counts. But MaxPoint has all of that data, so they have lots of demographic information, even down to the individual level, but we're not allowed to talk about that. It's public. It's not public, but it's legal. But in principle, one can begin to weave that into these terms. Okay, so let's just do the simplest thing today, because this is what we did a year ago in this paper. And the only covariate is the name, node I and node J. So we've got main effects, a log linear model, main effects, and first order interactions. We've only got the possibility of first order interactions. And here's the emulation idea. Oh, before I get to the emulation, what's this? Some of you may have seen this term. It's in a number of areas to do with networky stuff, flows of traffic, cars and bicycles between regions of cities, for example. Origin-destination flow is the term that's been popular there. Other areas such as epidemic spread, how is the epidemic spreading in terms of counts of of infecteds between spatial regions. This term has come into play. Gravity, well, I'm not going to tell you what gravity means. It's just a name that got associated with models like this with covariates back in the 60s, actually. And I did some work, actually, with NIST, National Institute of Statistical Science, back in the early 90s, using such models. So it's just a one-way analysis of variance. Okay. So let's do it. Let's back up and say, well, it's only 23 by 23, so I can do this. But now the 2400 by, I'm not going to do it. Okay. I'm not going to do it. So because these are the things I want to do forward sequential analysis fast on larger and larger networks. Okay. I can take a moderate-sized data set and go offline and do a big MCMC. How we want to do that? We want to be in the forward sequential scalable context. So we're not going to do that. We can't do that. Some of the work well, a long time ago, and I did that, but it doesn't scale. So what are we going to do? We're going to do model emulation by recognizing that in this flexible family of decoupled models that are just tracking stuff individually into nodes and between nodes over time, we've basically got a 1-1 map to the one-way analysis of variance, okay, modulo some aliasing constraints. So let's just center these effects at 1, okay, so 0 on the log scale, usual ANOVA aliasing constraint. And then we can just map. If we know the phi ijt's, we can just find mu, okay, geometric mean, and then find the alphas and betas, geometric means node by node relative to the overall flow, and then find the interactions, okay? And you can do some empirical stuff, but lots of these x's are 0, so you can't do that very well for most of the data. So this is emulation. We fit these flexible models, flexible decoupled, recouplable models that are able to track and understand variation over time and characterize it. And now we want to say, well, what does it mean in terms of node-node relationships, interactions? Well, let's just map over. It's just a 1-1 map. Okay. So that's emulation of a slightly more complicated model. So a few pictures. This is the strength of the node inflow transitions to nodes j. J equals 6 different values here. This is inflow through the morning period on February the 21st, 2015. So it's relative to 1. So we're about 12 times the average across the network, the geometric average across the network to the home page, not a surprise. Nobody goes, very few people go to science in the morning. The crosses here are just empirical flows, marginal flows, but there's lots of holes in them because of the zeros. You see that over here. And this was the one I showed you earlier, the world. There's some variation here. It's about 20% up on average in terms of being an attractive site in the morning, and then it goes up to about 80% above. So there's some variation over time, and some are more stable. From the point of view of understanding classes of nodes, I'm not a community detection guy. That's not it's just a way of beginning to look at the data and understand patterns. You know, yellow is high, and dark blue is low, and this sort of funny cyan color is right in the middle. So, and these are not on the same. These are all on the same scale. They're not on their individual scales. So, you know, people go to Weather and Magazine and a few other miscellaneous sites in the early part of the morning, and then it sort of relatively dies off to the later part of the morning. And it's vice versa on things like homepage, world, politics. It builds up throughout the morning period. In terms of putting stuff out, you can look at similar categorizations. The point I want to make here is there's a lot of action in the interaction. So let's look at a couple of examples. We like to call the interactions affinities. You know, the affinity of node J for node I and node I for node J. Time-varying affinities rather than interactions. So here's traffic from homepage to science. Very unpopular homepage. A very unpopular web domain on Fox News. But it includes everything. You know, it includes medicine. And I think most people probably go for medicine and health rather than other parts of science. So the simple smoothing model and the phi's over time convert to the relative probabilities. You can see it's a very unpopular. This is the probability of leaving the home page to go to science throughout the morning period. You know, 0.003. Second row is the alpha and beta. So this is the output from home page, which increases during the morning, and this is the attractiveness of science for anything, which is very flat at this 80% level throughout the day. And this is the affinity, the interaction. And I put this one in because, well, for a number of reasons, but one reason, for people who are interested in larger models where data is going to be sparse, you know, in a temporal context, sometimes that sparsity is different than at other times. Okay, so I'm going to put up the term dynamic sparsity. This is not a model for that or of that, but this simple dynamic modeling approach has, of course, the ability to say, well, look, traffic was depressed going from home page to science. It's low in the early morning period, but then it increases to about average in the interaction term, whereas these other guys are fairly stable. And this is just sort of assessing, well, is there an interaction or not? Because if it's one, there's no interaction. Okay, and you know, the latter half of the period, it's gone. I need my glasses, Francoise, but I didn't bring them with me.
1 minute.
Okay, all right. Well, since I've got 1 minute, let me just make this point. I won't go into the theory. So, in time series for decades, if you're in the business in Bayesian time series, forward sequential analysis, whatever your model is, all right, stuff is changing. You've got a model that says things are changing, but then things happen, right? Unexpected things happen. Your model's hopeless. Okay, it's been okay until now. So you see something that you don't like. Well, you know what's going. It's just a rare event, right? Okay, no problem at all. Oh, there's another one. Okay, so in the forward sequential analysis in time series, you know, the communities are very involved in their models and they do things. They jump in, and the underlying methodology of in the paper for this is forward sequential Bayesian predictive model assessment using Bayes factors in a formal Bayesian decision theory context. That is, I'll say standard here, standard in sort of linear Gaussian sort of systems in economics and business and other areas. But it's very, very useful in other contexts. And it's, with respect to the first desideratum, it's just a simple, trivial computable overlay on the analysis that we've presented. So I'll skip through that fun stuff and get back. You can read the words. I'm using up I'll give you 10 of my seconds in my last half minute to read the words. And just point out, just reiterating some touchstones that I mentioned earlier. It's a bit of an old project now. The current project is much larger, and it's basically taken 3 months just to put the data in the right, what is it? To munge the data. And we're there now, and we are running computers. But we're running GPUs, 2400 squared, and it's all very nice for a GPU, and it's much nicer than using clusters. We do the log linear model, the volatility model, the very simple random walk model, is the simplest example, the simplest non-trivial example of a class of dynamic generalized linear models. Okay, and so putting covariates in there is, quote, standard. Okay, putting in information about the regional mix of people in each node, for example, how is that influencing the traffic flows? Putting in known intervention information, how is that influencing things? Doing that on different days with a series of designed interventions. That can all go into the decoupled models. And also, I threw this one in for those of you that may have been at my talk last week and may see the Turing lecture, a very different topic, but there are also interesting variants of that where you use some of the n's and the x's from the last instant or maybe the last few instances to capture more of the local dependence structure. And that's just random effects. Okay, thank you very much for your time. Sorry to abuse the time a little bit. This is Rob and Jewel. Rob moved from Max Point to Boston to the Sync project. And most of the work here is Ji Chen. She's a fourth-year PhD student. And Karu, who just graduated. And my colleague, David Banks. Hopefully, JASA will get done with the tortuous process they've had us under for a year and a half. But of course, it's archived if you're interested. Thank you very much.
Excuse me, could you show again the plot where there were the four discrepancies one after the other? I just wonder if you have a parameter in your model which controls the reactivity so that it can adapt more rapidly.
Which plot?
This one? For example, this one.
Yeah.
Okay. Then the model follows slowly and make an average of everything. Do you have a parameter which controls the reactivity so that it can follow more rapid changes? Obviously, you cannot go too fast, otherwise you get nothing.
So the current, what is implemented and being evaluated in different contexts in this model, I mentioned at the start, so there's a single parameter that controls this volatility.
Yes.
There's an underlying Poisson, think about it as an underlying Poisson rate. Okay? Although it's now mapped over to a more interesting model. There's one parameter that controls that. When it's high, it's very stable. When it's lower, it's more erratic. So what's happening here? This is a level shift. There's been an impulse and things have shifted up. Or it's just a pretty rare event of four slightly wild and highly positively correlated deviations from predictions. Or it's a manifestation of just more volatility and they just happen to line up by chance. Okay? So one simple way to model that is to say, well, look, let's find out. Let's allow for more volatility and see where over the next 2 or 3 time points the model takes us. Okay? And that's really the philosophy that lies behind this. The other point is that there are immediate variations of this that instead of being locally constant, random walk is locally constant, right? Are locally linear and follow things in time slightly better when this sort of thing happens. But we'd rather just skip that and begin to expand on bringing covariate information in, because that's what the project's really focused on.
Question. So when you do this decoupling, you're specifying and fitting marginal distributions to different parts of the whole joint distribution. So when you fit like all these node-specific models, there's a chance, I would think, that they aren't coherent with each other, that they don't specify a valid joint distribution.
Yeah, conditionally independent, so they're perfectly coherent.
Even when you have flows, when you're modeling flows
Yes.
from one to the other?
Yes, flows coming into node, we're assuming that the inflows to nodes are conditionally independent, conditional on rates. They may be dependent, those rates may in fact be dependent, but we're looking at posteriors that assume independence, so we could look at that, okay? And we could model that if we wanted to, but we're not doing that here. And then the outflows from nodes are conditionally independent. There may be dependence in terms of outflows. It may be that all of a sudden everybody wants to go to one particular node. Okay, we're not modeling any of that. No. Yeah. That's where covariate information would come into play.
But I would think like inflow to node I depends on how many visitors there are at all the other nodes, right?
No, inflow from the outside world.
From the outside world.
Okay, it's the multinomial transitions within the network that deal with that dependence.
Okay.
Thank you. Thank you.